Hello, it's Keith here, and this is the final episode of the Grime 68000 series. Now, the programming was finished in the 7th episode, and today we're going to look over the source code. I'm going to describe the finishing state of it, so that if you want to change the game yourself, you can do so, but if you're not really interested, then at least you can see what the game is actually structured like for the system. Now, the 68000 version was based on the Z80 version, as was the 6502 version. Generally, they're all the same, but either way, we'll just look through it all, see how it works, and I'll tell you some of the interesting points that are worth looking at as we do. So let's just close these and let's actually have a look at the code. So here's the start of the program code for Grime 68000, and the first thing you'll see is this tall tile command. This is exclusive to the X68. It has no function on the other versions. All of the tiles are 8 by 8 pixels. However, on the X68, that gives them a rather squashed appearance because the minimum resolution of the X68 is 256 by 256 rather than something more conventional like 256 by 192. So there's an alternate mode which uses 10 pixel tall tiles by doubling two of the lines within the tile. This is optional, and remming this line out will disable it. On the Neo Geo, we do need to define a special variable called vblank count, which isn't needed on any of the other systems. This is used to detect the refreshing of the screen and is used for the pause command to know when a frame has occurred to keep the game in a reasonably regulated speed on all systems irrespective of processor power. Then we've got cursor X and cursor Y. These are to do with the text cursor. They need some RAM allocated to them. And then we get to the actual variables relating to the main gameplay. So we've got tile map here and tile map 2. As with the other systems, tile map 1 is the visible tile map. Tile map 2 is the last tile map. This is used to detect changes so that only changes are drawn to the screen. Now, one interesting thing to notice is there is a gap of 256 bytes here. This is because the tile map needs to be byte aligned so that the last 5 bits are 0 at the far left hand side of the screen, so that because parts of the code use that to detect the X position of an object when it's comparing the tiles. Now, because the 68000s allocate memory in a fairly unpredictable way, I'm actually blanking those bottom 5 bits, so we have a buffer of sort of 256 bytes here that are unused because it's possible that some of those bytes will be needed by that tile offset. Now, 256 is far more than I actually needed, but we're in 16-bit territory here and memory isn't exactly short, so for playing it safe, I allocated 256. So then we've got our two tile maps, 768 bytes apart as usual. Key presses aren't actually used, this was all copied straight over from the Z80 version. X position of the player, Y position of the player, random number generation, the last value is stored there. Fast growth is used to accelerate the growth of the grime if the player hasn't been playing very much recently. Player direction, that's the direction the ship is facing. Bullet X and Y, nothing shot is how long it's been since the player last shot anything. This is to do with the fast growth again. If they've not shot anything for 32 ticks, then they're slacking off. We drop some more invaders in and accelerate the growth. Allowed fast growth, that's again relating to the enabling of the fast growth. There's two stages, allowing it and then whether it's actually in play at the moment. Bullet direction, that's the direction the bullet's moving. Playing sound effect. Now, the driver chibi sound, which I wrote, does the sound effects. It's a single byte value that defines the pitch of the sound effect being played. Control mode is relating to the 1 and 2 fire mode options that the game has. Some of the systems only have a single fire button, others have multiple fire buttons, and there's an option to either hold down fire and push in a direction to face that direction, or to rotate left and right to fire. You actually fire continuously in the game. Game tick is a variable that just constantly goes up. It's a single byte, goes round and round in circles, so it's used for some events that only want to happen at certain times. Lives is how many lives the player has left, obviously. Animation frame. This toggles between 0 and 16 to flip in the alternate tiles to allow for 2 frames of animation of the tiles. Only simple animation in this game, only 2 frames. The score is a 4-byte binary coded decimal 8-digit. It's packed mode as it's called, and the high score is the same. So these are just used for the score and the high score. Animation tick is relating to the redrawing of the screen. When the screen is being redrawn purely for animation, it's done in 6 stages to reduce the amount of drawing that goes on at one time. So that's the tick that's currently being redrawn. Debounce is relating to the fire buttons on the faster machines when you're using that rotation mode. If this wasn't in place, you would press left and it would register potentially 2 ticks. So you'd turn 180 degrees before you'd seen that you'd turn 90 degrees. So this just stops that from happening. Random seed 2 is another part of the random number generation. Now, parts of my code were using IXH and IXL on the Z80. I was doing a very crude mapping of the Z80 registers, so the 68,000 registers, and because I was using a crude mapping, I ran out. So for simplicity, I just allocated some memory to the extra registers I needed here. Speed wasn't an issue. So here we're defining the default control mode for all of the systems, and then we're defining the palette. All of the systems are 16 color, at least in the way I'm treating them. Of course, the Neo Geo is 256 colours, but we're only using 16. Turning the joysticks on the Atari ST, setting the default control mode after the reset, and here we're loading in the Genesis tile map. Now, 3 of the systems are bitmap, that's the Atari ST, the Amiga and the X68. The Neo Geo is also tile map, but those are tiles in ROM, which we don't need to load into graphics memory because the ROM is always graphics memory, so it's a swings and roundabouts. It's a bit annoying in some ways, but it means we don't have to load them in. Then we're clearing the screen, setting the system to redraw everything, and then we're loading in the title screen from the definition at the bottom of the file into the tile map so that it can be drawn. Then we're showing the message to the screen. It's the same as always. We have a counter that works out the first character we're going to show, and if we're skipping less than 32 characters, then we have to move across to the right, and then we start drawing characters. If we've shown all the characters, then we pad out the string with spaces, which is character 32 here. I've been over it quite a few times. It's not really any different here, but it's quite annoying. Unfortunately, getting it working was a bit of a pain, but it does work. And then you've got a pause here and an animation of the screen, and we're also altering the random seed because when the player presses fire will be a random event, so let's use it for random number generation later. So here the game starts. We set the score to 3, we set the score to 0. Because this is a 32-bit system with regards to its registers, it can write 32 bits at a time. We can clear the entire score with a single command, which is quite nice. And then we clear the screen here. We paint the screen. This is the start of a new level. This is the start of a new round, so to speak. And then we position the player in the center of the screen and the starting position of the bullet. We set the direction to the default. And we start with some fast growth. So the grime is going to grow pretty quickly, so the player has something to be challenged by. Then we create 2 invaders, which will appear at the far right of the screen and drop the first of the grime. Then we reset the game tick here. Now this is the main game loop. We are going to get a random number and we are going to use that to decide if we want to create an invader or a descender. They appear at random times. They also appear if the player doesn't shoot enough stuff. Then we see if fast growth is occurring. If it is, then we automatically do an evolve. Otherwise, we check the game tick and decide whether we're going to do an evolve. That's where the grime gets bigger. A move where the grime starts where the seekers start chasing the player, or a pause where nothing happens at all. So the pauses are done with the vblank command. I've got a command on each system that waits for vblank, which is the refresh of the screen. So the frame rate is limited to 60 FPS. Then we're coming to processing the player. The first thing we do is we show the score and the lives here, and then we check if anything's been shot recently. If it hasn't, because the counter's got to 31, we create 2 invaders, the descender, and we allow the fast growth, which means the player's going to have a bit of a challenge ahead of them. When we get here, we set the marker of nothing shot, and then we load in the XY position of the player here, find the tile, and we check the player's position. This is the same as on all of the other systems. We're just making sure if the player is trapped on all sides. If the player is trapped on all sides, then they're dead. That will cause the execution to get to this point. If at any point they are not trapped on a side, then the execution will jump to player still alive. Now you'll notice we're using push and pop BC here. There's no literal BC registers on the 68,000 systems, but I've mapped each one of the registers the system does have to a virtual register on here. So whenever my original code was using B or BC, I was using D1, or A1 if I was using it as an address. DE was going to be D2 or A2, and so was D. But if I was using C on its own outside of B, then I would be using D4, and that's why I ran out of registers for my XH and IXL. But as I say, there's this push BC and this pop BC, and they are just some macros that are being used to emulate that functionality with move commands to the stack pointer. Now here we're clearing the sound effects so that we don't make any sounds, and then we're checking what control mode's being used. This is the single fire mode, which is where we have to check whenever a direction's pressed to see if a fire button is also pressed. If it is, we change the direction. If it's not, then we actually move the player in that direction. So you see here we've got these face fire up options, and we're loading the direction into D6, and we're altering D4 and D1 if the player is actually moving, because those are the equivalent of our BC registers and D6 is the equivalent of our L register if we're comparing to the Z80. Here's the 2 fire button mode, much simpler version. The directions just move the player, and then you've got some rotation commands just here. We're just altering D6, checking if we've gone over the limits and rotating it around if we have. So D5 here, we're just checking if it's non-zero here, and that's how we're doing the rotation of the player. When we get to here, this is the pause button, so you can pause the game. Then we're just updating the position of the player here. If the player has moved, then we need to redraw the player and wipe out the old player position. And then here we're just doing the bullet. Now the bullet sequence is done multiple times, and so we're doing it 4 times, and that's being moved into this fake IXL register here. And then what we do is we check the direction, we move the bullet, we see if the bullet's hit anything, we run bullet strike if it has, and then we keep repeating that 4 times for each visible frame. That's because the bullets have to be much faster than everything else, otherwise you're going to have no chance of keeping that grime at bay. And then we draw the bullet. If the bullet's hit anything or gone off the screen, we need to restart it. We always restart it at the position of the player, so that's what we're doing here. And here we're just redrawing the bullet, which is sprite number 5. Then we're loading in the player's position. We're just updating the new position of the player here, and then we are playing the sound effects here. This is the bullet strike code. We work out how much score the player needs to have added. The scores are at the bottom of the code as well, so they're in the same binary coded decimal format as the score itself. Then here we are just updating the score. We are then removing the bullet tile and the enemy, of course, and then we are just setting that the player has shot something recently and stopping the fast growth if it was running. Then we get another random number. Every time we pull a random number from the random number generator, it kind of re-randomizes it. So again, we've got a random event here of the player shooting something. Let's use it for a bit of randomization. Mold evolve is where the mold starts to get bigger. So we loop over the entire tile map. We have to work out where the exact tile map is, because it's got to be, as I say, the bottom 5 bits have got to be set to 0 here, otherwise the code won't work properly. So that's what we're doing. This is all just a rather painful bit of code to load the tile map into the register. I mean, originally it was just load tile map, HL, and that was it, but in this case it's a lot more complex. So that's what we're doing there. Then we are just checking what kind of grime the current tile we're looking at is and jumping to the position that will handle that kind of grime, and then we are just repeating here. Mold move is a simpler version because this doesn't evolve the mold, it just does the fast moving objects, the invaders, the descenders and the mold. Otherwise it's identical. Descenders come down the screen. They change the mold as they go over it, so we're comparing what the original mold was, and then we're changing the colour accordingly. This has a kind of inverting effect on the grime, and it makes the grime a bit more complex and sort of switches the seekers to the blue mold, I believe it is, and it kind of puts kind of blockages in for the mold seeking you, so it's quite fun. The invaders come from the right and go to the left. They also drop the grime. So this is the code that will actually handle the invader movement. We have to work out the current column that the invader is on, and if they've gone off the screen we need to remove it, but if they haven't, then we need to check if they've hit the player. If they haven't, then we have to work out what's underneath the invader and see if we've got a random number here. If the random number matches our expectations here in that it's 0, then we're going to drop a spore of mold. The mold spore is 8, and that will drop more mold onto the screen. Here we've got to the end, so we just save whatever we are now putting underneath the position the invader was on, and then we return here. This code will remove whatever was currently being processed. This is used in various places to remove the current object. Mold seek, this is the seekers, the yellow things that fly towards the player. So what we need to do is read in the player's position, work out how the seeker's position compares to it, and move them closer to the player as appropriate. We do this for X here, and then for Y here, and then when we get down here, we just update the new position of the seeker. Seekers can't go through any other objects, so they always check if the new position is 0 or not. If it's not 0, then it can't go to that position. The green and blue mold use the same code because the logic is basically the same. The center object becomes a new color, and the outer 4 north, south, east and west objects become the color of the original object. So that's the logic, and both use the same code, but we just move the new tile colors into the fake registers here, and then we run the evolution code. The evolution code uses the byte-aligned nature of the tile map, and this is why I had to do that trick with regards to offsetting the tile map and wiping the bottom 5 bits to 0. And so this will check the position, make sure if the grime can expand in each direction, i.e. it's not at the edge of the screen, and also if there's nothing under the tile map that can not be affected, and it will expand appropriately here. This is the repaint screen code. The screen is repainted in 4 chunks, and if you think of a 2x2 square, each corner is done separately, so the fill command is run 4 times. This is to make the fill more neat, because if it was done as a vertical wipe you might see that, but if it's done in a checkerboard pattern it's not very noticeable, so it was the more efficient way of doing things. That said, tiles that are changed are only updated. So what we do here is we scan the entire tile map and we work out the position of the old tile map by adding 768, because tile map 2 is 768 bytes away from tile map 1. That's a requirement. We compare the new tile map here with the old tile map, and then if the tile is unchanged we skip over the next bit of code. The next bit of code updates the old tile map with the new tile and redraws the tile. In a great number of places we use this find tile command. This will take an XY coordinate and work out what memory location that tile is using, and so we can there in that way detect what's the player's shooting, or what's under the player, or if we need to create a piece of mold in a particular position we can use this command to do that. Find tile alter, well, this was never actually used in this version, but find tile kind of falls into this. There was a version for the alternate tile map I think at one point, but that's just legacy there, just ignore that. Render tile does the actual drawing. Very straightforward command on this one. It just runs the find tile command, which we'll look at in a moment. It does all in the animation frame, which if you remember is 0 or 16. The code does limit to 16 possible tile combinations, and so that's all that does. And clear screen just wipes out the entire tile map, so it's a fake clear screen. It's not a literal graphical clear screen, it still uses the tile map. Force repaint sets the entire tile map 2 to 255. There is no tile 255, but what it says is to the system is I've got to repaint the entire tile map next time I draw. Force animate, this is the tiles wouldn't naturally animate until they moved, so there wouldn't be any animation. What we do is we scan through 1/6 of the tile map, moving in 6 tile groups, and we force a refresh of some of the tiles if they're non-zero. This has the effect of making the grime wobble, but rather than it all moving at the same time, slowing things down, only 1/6 of it moves each tick. So this is a way of doing that. And so we scan over the entire tile map, we check if the tiles are non-zero, and if they aren't, then we change the alternate tile map to force them to be redrawn. And you can see that just here, and we redraw them by setting them to 255 in the alternate tile map again. Here's the pause command, we just wait for vblank. And here's the debounce command. What the debounce does is it reads in both controls, and if anything's being pressed down it waits until it's not. This is for the game over screen and things like that, where we need to wait for a fire button to be pressed, but we don't want the enthusiastic player to be still pressing the fire button down from before. This is the code to create a descender. What it does is it takes a horizontal column, and so it just gets a random number. It keeps only the bottom 5 bits, and that will be a value from 0 to 31, which will be a column number. We then set the tile map on that position to number 12 to create the descender. The invader code is kind of similar, but it needs to be a row. So what you have to do is you have to multiply by 32, and we do that by this rotate left command here. We do have to clear the bytes of the tile map as usual, and once we've done that we just load in the invader, which is tile number 11 here. This is the player dead code. This is the same on all of the systems. What it happens is the grime kind of melts down from the top of the screen, a bit like the old Doom game, and the way we do this is we pick a random number out of the system. We treat that to be a column number. We then scan that column to see if there are any positions which don't have the game over grime, which is tile number 13. If we find one, then we fill it with that grime, and if we don't, then we just carry on. So this will pick a random column, it extend the grime by 1 position on that column if it's not already at the bottom. This of course doesn't guarantee that all the columns will actually ever get filled with grime, so to get around that problem, what we do is once we get to the end we just force fill the entire tile map with that tile 13, which gets around the problem. This rather long nasty gunky code here is actually working out what sound effect to play. There's a kind of descending sound as it happens, but I'm sure that could be made better, but I haven't done it. So when we get down to here, we pause the game here, and then we decrease the number of lives. If the players run out of lives, then we're going to show a game over screen. Otherwise, we're just going to restart the round. The game over screen is just a game over message with an adequate insult for the player there. And then we see if the player's got a new high score. If they haven't, we just jump over to here. But if they have, then we show a high score message and we update the high score. Again, this is something that the 68000 can do very well with its 13-bit registers. We can update all 4 bytes in one go. The Z80 had to do an LDIR command for this. This is the random number generation. It's basically the same as the 65021 one. I don't know the way of doing proper random number generation on the various machines. I'm sure there's great ways of doing it, but I thought for a laugh I'd convert the one straight from the 6502. So this command is basically pushing and popping all of the registers in the system with the exception of D0. Then what I'm doing is I'm loading random source, which is a set of 8 random bytes at the bottom of the file, and then we are storing that in A4. We're loading in the random seed. We're picking in a value from 0 to 7, and then we're picking one of the values out from random source using this rather complex command here. This is a fixed offset of 0. This is address 4, and then we're doing an offset of D from A4. So we're going to go over these in the tutorials, but this is one of the more advanced offsetting commands, that indirect commands that the 68000 can do, and it was quite fun to use it here. We are EORing that with the random seed that was used last time, and then we are doing the same again with another 3 bits here, again with A4, which is the random source, and then we are EORing that with the last result as well. Finally, we're getting random seed 2, which is another random number generator we use, a source of random number generation, sorry, and then we are using the game source code itself and doing the same again, picking a random byte from the source code to use as the possible random data. Finally, we're limiting it to a single byte to match the functionality of the other systems, and we're just returning. And then here we've got the general functions that are being used for the game. Here's the font used on all systems except the Neo Geo. Again, it's in the ROM otherwise on the Neo Geo. And here's the sprite files for all the systems except the Neo Geo. Again, as I've just said, because they're in the ROM of the Neo Geo, which is specified by the XML file that MAME uses. Here's the random number sources, all 8 of them. Here's the palette. All of the systems use the same palette in this case. These are the binary coded decimal high scores that are added. This is the title picture that says Grime 68000. These are the direction buttons as they are reported by my joystick reading software. Here are the people who are kind enough to back me on Patreon, and the thank you message and the title message. Here's various other messages that are used. All messages in my games are 255 terminated. And then this is the RAM area. This code here selects the chip RAM on the systems that need it, but basically this is just allocating some memory for the game's variables. These are the sound effects that are used on the Amiga because they need to be wave data in the chip RAM. And then we've got the footer of whatever it is, whether it's a disk image file or a ROM image or a cartridge. The footer program I've created here just deals with that. So finally we're going to go over Simple Tile. Simple Tile does all of the graphical work of the actual tile map. It doesn't do the fonts, but the font code is fairly similar. So what we're doing is we're loading in a 16 color tile from whatever the system uses, or if it's a tile map system, it's actually just updating the tile map accordingly. So on the Genesis here, we're having to work out the X and Y position of the tile that we need to update, the correct memory address. And then when we get down to here, we are specifying the next address we want to write to in D5 here, and then we are specifying the new tile number here starting from tile 256. The font is allocated 128 tiles, but why not? Let's just start from 256 to be clean. And then the Neo Geo version is kind of similar. The mathematics to work out the memory location are different here, and the way we write is slightly different, but basically we just need to write to this address with the address in memory that we need to write to, and then the new data for that address here. And the tile map definition is a little bit more tricky maybe here, but we are having to add all of this to the tile number. So those were the tile map based systems. The remaining systems are bitmap based systems. So we use get screen posit to work out a memory location from an XY coordinate, and then we are filling in the data accordingly. Now you'll notice here things are a bit weird on the Atari ST, and that's because the Atari ST works in words. Now my exporter, my Sprite editor, which you can download for free, which is this thing here, this exports on the Atari ST in words, so it exports in 2 byte pairs. Now unfortunately that's not very appropriate for this software, because this software needs to work in 8 by 8 tiles, whereas the exporter was working in 16 by 16. So what I'm doing is I'm skipping over some of the bytes here, and so this is working it all out, but it's just a little bit clunky, but it's perfectly adequate for this anyway. And then the Amiga version is a bit more straightforward here. We're just working out the memory location in the bitmap that we need to show, and then we're writing the bytes to the 4-bit planes of the Amiga. We're going to go into this in more detail in specific graphics tutorials for these systems, so I'm sorry I'm being a little bit quick on this, but I don't want to go into sort of too much detail here because I need to do a lot of research on it to make sure I'm telling you everything right, and I don't really have time at the moment to do that. So we're looping around each of the lines here, and then once we're done we just finish off here. Now the X68 is actually kind of the most straightforward. It uses, if I remember correctly, it uses the same format as the MSX-V9K actually, I think, but it's a very straightforward format. So we're just writing the bytes to the screen. The only slightly tricky thing is that we've got this tall tile option here, and what we're doing if we're using the tall tile, if we're not using the tall tile, we have to move everything down by 3 lines to centralize it. But if we are using the tall tiles, then what we need to do is we need to work in groups of 10 lines rather than 8, because our tiles are 10 lines tall now. We need to draw 10 lines of the tile rather than 8, and we need to repeat lines 2 and lines 5, and we do that by subtracting 4 from the address as we're writing, because we're reading from this address here and we're writing to this address here. Now the data works, it's quite odd, only the bottom nibble of each of the addresses is used in the destination, so you'll see we're updating the destination twice, but we're updating the source only once here, just here. So that's why that is, and there's a rotate right here to compensate. So I mean, arguably I could have doubled the amount of memory that the tile map was using, and then reduced the amount of time, because then I could have done away with this ROR, but I'm not sure that would have actually been faster, and this is the way I ended up doing it. So as I say, I apologise, that was a bit of a quick summary of the graphical routines, but I will go into it in more detail later when I've got proper tutorials covering it and I can give better graphical demonstrations and things. But that's the basics of the Grime 68000 source code. So as I've said before, this is all free, open source. I totally encourage you to change it, do whatever you want with it, make your own games from it, make better games from it, because it's supposed to be something simple and fun that people can just make a start with, because as I've said before, Vasen, the assembler I've used for this, is free as well, and this is Notepad++ you're looking at now, which is also free. So nothing I've used in this is something that you can't get and use at home, so go ahead and have some fun. But I hope you've enjoyed the Grime 68000 series, and if you've not seen it, check out Grime 6502 and Grime Z80, because Grime as a game is currently running on 25 systems, and who knows, maybe it'll turn up on a few more if I get enthusiastic later. Anyway, thanks for watching this video today, and goodbye.